Welcome to the Tom Nelson podcast. I have Kevin Kirchman here, and I have been a believer in the greenhouse theory myself. Kevin is going to do a presentation showing why that may be wrong. Kevin, you want to introduce yourself and get us started here?
Sure, Tom, thank you. Basically, I'm challenging the greenhouse gas theory. This will explain why I'm challenging the greenhouse gas theory, or what was my motives, so that you understand that. My father founded a software company in the 1960s, so I grew up in the software business and learned to program young, like a lot of people have done. And what I found is that, well, if your program doesn't work, it's because it's broken. And so you either fix it or you throw it away. So when I encounter a theory, if it doesn't work, then either fix it or throw it away. And later I went to Cornell, but I got an AI interest back then. I don't have to explain that. But at Cornell, I was at grad school, and my thesis was AI applications in engineering. And I concluded that without a science of knowledge, which is called epistemology, we would never have successful AI. Well, that's kind of true. We have neural networks, and they've been pretty cool. So they've done a lot of damage in that direction. I decided I want to figure out how to develop this science of epistemology that I felt was possible. The classical challenge of epistemology is, how do we distinguish between knowledge and opinion? Okay, so the ancient Greeks were looking into that. Today, when we go on the internet, the first thing we want to know, is this rubbish or is this some knowledge that I can use? So this archaic idea of distinguishing between knowledge and opinion is not so archaic. And everybody's concerned about it because we don't want fake news, we want real stuff. And so a lot of people are talking about it. So this is addressed by the challenge of epistemology. So it took me about 10 years to develop this broad-based new epistemological theory. Fortunately, I discovered an underlying order in the nature of conceptual knowledge that could serve as a foundation for a science. I call the concepts, or the P plants of epistemology. Now, what I mean is Gregor Mendel used P plants to develop the science of genetics. And he discovered an order there that he could then explain and provide a basic explanatory paradigm, and then genetics as a field evolved. Okay, I used about a dozen books. I was in a remote location with a small business that I ran, so I wouldn't be worried about anything but staying alive and working on my epistemological work. And each sentence is basically a concept. In a book, you have about 300 pages and maybe 30 or 20 or 30 of sentences on this page. So you get 6,000 to 9,000 concepts in a book. And I had 10 books, so I had 60 to 90,000 sample size. And these books were just general books from different subjects, and they weren't contorted to conform to some epistemological bias. They were just written about their subjects by various authors. So it was a good sample set. And my drive in the epistemological challenge was, I had an idea. So my idea was, hey, what if I make explicit all the knowledge that's inherent in a given concept, all the semantic and syntactic knowledge in a given idea? And I did this by creating a symbolic representation called the general form of a concept, into which I would convert any given concept, and then go through each of all those nuances of knowledge that were represented and asserted in the concept and assess their validity. So this is a method, this is a scientific method to assess the validity of ideas in the general case. Now, I later did a full historic and philosophic comparison of my work with the history of Western philosophy, doing independent study at Oxford and using the Bodleian Library, because this is in the mid-90s. And the Bodleian Library is one of the best philosophic libraries in the world, having started in about the 14 or 1500s or something. And so then I went to graduate school in philosophy of science at the LSE, the London School of Economics, which was founded by Karl Popper, who was pretty much the 20th century's foremost theorist of induction. And he basically founded the scientific method that's used today as theories of falsification. What I was fundamentally doing was similar to him in that falsifying an idea by finding out where the concept is invalid. Okay, so nonetheless, so I withdrew from LSE and founded my software company because I found I was explaining more than I was learning. and wasting my time. And so we built software using my new theory of deduction, new lexicological theory or theory of meanings, and the general form, the symbolic representation. And we were the first technology to deliver direct answers from live unstructured text off the net. And so we had clients like Litton Aerospace, Procter & Gamble, Baxter Healthcare, IBM offered to buy the company, attesting for me to the validity of this new epistemological science, because it was being used, and I took actual chunks out of the papers and applied them directly in software to do a real problem that was used, found a value to commercial buyers. Now, I was first introduced to the global warming theory, just looking at a BBC webpage and on just a regular page. And they had one day they put up the data on all the CO2 values and the temperatures over a long period of time. This is back 10 or 15 years ago. And so I was looking at that data and I was going through and I said, man, it looks to me like the CO2 is rising after the temperature rises. And it was like a 90% correlation. I didn't do a scientific assessment of it, but it was just like, hey, wait a minute, that's not right. The temperatures don't appear to be rising as a result of CO2, but CO2 is rising as a consequence of rising temperatures. So as a mechanical and aerospace engineering out of Cornell, one of my degrees is in mechanical and aerospace engineering, so I know heat transfer, and the other one is in computer science. And so I basically said, hey, wait a minute, maybe it's the solubility. And it turns out that the solubility of CO2 in ocean water falls when the temperature rises. So this says, well, that's a nice causal relationship, and it's very strong, it's very explicit. If you leave your Coke or fizzy can out on the counter for a couple hours, it'll be flat. And the CO2 doesn't take days or years or months to leave into the atmosphere. It leaves immediately. And the same with CO2 in the oceans. So you warm the temperature by a degree, and there's an increase of about 2.6% in CO2 in the atmosphere. Anyway, so that was more hints that there's something wrong with this theory. So then I said, hey, why don't I demonstrate the validity of my theory of validation? And so now I've confirmed my theory of deduction, my lexicological theory, my general form. Why don't I show that this new scientific method that I've devised actually works, and it's an improvement on our existing paradigm? Okay, so that's what that's my kind of motivation. I don't have any petroleum companies or anybody funding my work. I did this myself, as my bill. And but that was my motivation. So now let's get to the tearing this edifice down, because I think it's non-functional and it's not a valid theory. And even though the rest of the world says it is valid, I say, wait a minute, there's too many things wrong with it. But first of all, if it's not warming and CO2 is increasing, then that's a problem. And a lot of people are starting to see that. And we got Tony Heller's done a great job showing us that maybe NOAA is manipulated the temperature data, and they acknowledge they changed the data, but it's following a pattern that they're trying to increase the temperatures according to the rise in CO2. So they're basically, they're altering the data, which is atrocious. So it's a horrible thing. Anyway, so that says, wait a minute, that's strong evidence that this theory is invalid because it doesn't work. Okay, so now I want to understand, because there's still trillions of dollars, billions or whatever of dollars being spent on this poor theory. So we're gonna have to beat this thing to death if it is invalid. Okay, so I have to go in, or somebody has to go in and analyze this theory from the deepest levels of physical understanding and make sure that it's correct, or if it's not, why it's not. And so that's what I've done, and that's what I'm going to talk to you all about today. Okay, so I say the forcing concept that you've all probably encountered, to me, is pseudoscience. I don't care how many papers or how many people want to talk about this forcing or that forcing. All the influence on emissions are wrapped up in the albedo figure. And I'm going to explain that more thoroughly later. When the albedo rises, it's a measure of reflectivity, but also of emission. When the albedo goes up, it's a number between 0 and 1. If it goes up, that means the temperature of the Earth will fall. If the albedo goes down, it means more energy is being absorbed, therefore the temperature of the Earth will rise. That albedo incorporates things like CO2, things like cloud cover, things like snow cover, things like the dark roofs and more highways. Okay, that's all in the albedo figure, and we can monitor that. And I'll talk to you about some curious data issues with our measurements of albedo later too. Then I also want to discuss the time factor that I feel has been missing in our evaluation of Earth emitted radiation. And we want to know the rate of change of temperatures, not just the temperatures. And basically the rate of heat transfer varies to the fourth power of the absolute temperature difference. Now, the temperature of the Earth is one thing, and I'll show how we arrive at that, or how we should arrive at it. And then the temperature of space is about 3 degrees Kelvin. Okay, so that's the temperature difference. And that's a pretty strong, that's Stefan Boltzmann law corollary, basically. And so it is not possible for the atmosphere to slow heat transfer, because it's independent of the material. It's dependent solely on the Stefan Boltzmann law. But that material, however, that equation does reflect albedo, and I'll talk about that too. Finally, I want to, once you've stripped apart the greenhouse gas theory, you're going to have to replace it with something else. So then I'm going to discuss nitrogen and oxygen and their role as the primary stores of thermal energy in our atmosphere. And then as some real exciting, I'll dig into some major physicists of our time, as well as show why Einstein basically disagreed with them or gave them a warning that they didn't heed, and how that warning has caused the field to misunderstand the nature of scattering as a primary means of absorbing photon momentum, and that's because of conservation of energy. Okay, so and then I'll move forward here as your excellent interview with Richard Lindzen said. In attacking the narrative, we are accepting the narrative. So if somebody says, hey, the greenhouse gas theory says CO2 increases cause the Earth to warm, we can ask, well, is it just CO2? And then we start to talk about methane. And then we say, how much does it warm? Well, we've already gone down the path. And so we're starting to attack the narrative, but in doing so, we've committed to the narrative. Okay, so challenging the greenhouse gas theory is not accepting the narrative. Okay, and if we're going to challenge this problem, we've got to deal with the foundational. Okay, so this is another slight digression before we get underway. From my perspective, peer review is censorship. Now, Galileo, considered the father of modern science, failed peer review so completely he was given house arrest for the balance of his life. That's because he failed peer review. He said, when Aristotle, who was the scholastics endorsement, the Vatican said Aristotle is right at that time, and he said that heavier objects fall faster. Galileo says, wait. He used a clock and he rolled down some different densities down planes and he measured the thing. He says, no. They all accelerate at the same rate. So Aristotle is not correct. He also showed how Venus has phases and that it was revolving around the sun. Oh, the heliocentric view was endorsed in his time. So he got in big trouble for that, and sadly, but he still had a huge influence as a father of modern science. Okay, so I see peer review, it's promoted as a type of quality control, okay, which is, from my perspective, is a crutch. And it's sort of like, well, tell me what to think because I don't want to figure it out myself. Yet there's so many other ways that we can allow people access to knowledge, and we can let people endorse them. We can look at who endorsed something. We can use those as cursory. We want to know the subject. You know, if you're an expert in emissions, do you want to hear about the blue-footed booby or whatever? You don't want to look into ornithological papers. So this is the manner in which you go and you drill down, you find out what's interesting to you, which subject, which field, which particular things are relevant to you. You do need somebody to help. It doesn't hurt to help somebody collate those, but we ought not to be peer reviewing and looking for somebody else to tell us what to think. We, as scientists especially, we are supposed to be the expert thinkers, the people with the most profound grasp of knowledge and the most capability in determining and creating new knowledge and assessing the validity of existing and new ideas. Okay, so peer review can be used also by incumbents to protect their own research and funding. and who are afraid of contrary and competing views. Okay, so those are reasons why we've got to challenge this peer review idea. And then finally, I use the indulgences, which was from the Catholics. They used to, you could pay to get into heaven, you know, that's Galileo's time. So out of respect for Galileo, we shouldn't be paying for reviews to get into journals. And that's sort of the idea behind my founding of the Climate Science Journal. Okay, so one last thing, this is important. If you want to learn about something or have questions about it, you need to become familiar with the technical literature. Okay, that makes perfect sense. But it's important to recognize that once you do that, because it's very complex and broad, you will likely be caught in its embrace. And that's in an Oxford professor of philosophy's comment. Okay, and then finally, before we get into the better part of this, reason isn't like hauling rocks, because that's just not what it is. A single horse can outrun 100 wagon pulling horses, as Galileo has explained for us. Okay, now I want to give you a kind of a summary view of where we're going, and just give a little bit of background for people. This is is my chart here of the solar. The red is a radiation coming from the sun, and the blue is the radiation leaving the Earth. Now, in a temperature equilibrium, those two have to be equal. The areas under both those curves has to be equal. But you serve one is really tall and one is really spread out. Okay, that's the energy. So this is, normally you'll see this graph in logarithmic form, but that causes you to misunderstand the relationship. So when we pick out a few wavelengths of Earth IR radiation, well, we got to remember that really that IR is spread all over the place. And that's just the way that because it's a cooler body, that works. And so we have to be careful that we don't attribute too much to those windows where we think it's blocked. And I'll explain more that it isn't. Okay, so here again, we're now moving into the details. So there's another sort of a misconception. Okay, see this black line here? Let's call it it's a black body temperature, and you'll see that often when you'll see a spectral analysis of Earth radiation, for example. And they just put it on there it's a comparison. Okay, this blue is the energy that leaves the Earth. Okay, so this is an Earth spectrum, not a solar spectrum. Okay, and so over here is as many people have acknowledged, is the region where CO2 is not letting the energy leave the Earth. Okay, so that's what they're saying it's blocking. Okay, and then again, this temperature for me is too high. Okay, now I want to go and explain that this doesn't actually make sense. Okay, so what really should happen is that the area of this blue region, where it's just the emission spectrum, should be equal to the area under that line. That comparison line this green is an approximation, so it's not perfect. But basically, the area under this green line should be equal to the area under the blue line. Okay, because that means that some of these spectral regions here exceed what appears to be the temperatures of the Earth. It's because the whole of the Earth emissions are the basis of how temperature is calculated from the black body. We're starting with the black body here, and then I'll drill down a little bit. So the Stefan-Boltzmann law says that the entire emissions are proportional to using the Boltzmann constant there, are proportional to the temperature to the fourth power. Okay, so so fundamentally, if this were to hold, right, then any increase in the blocking of by CO2 in the blocking of emissions by CO2 would lower the Earth's temperature, right? So let's just say this went down a little lower here, then that means that the temperature of the radiation, effectively calculated from the radiation, is lower. So there's a little bit of a mistake here, because that can't be right. The CO2 rises and then there's less radiation. Okay, so that's weird, because that would mean the temperature is lower, right, of the Earth. Okay, so let's keep going. All right, so we arrive at this Okay, so I've just explained that, and now I'm going to go right to something. Okay, so something is missing from the above equation is basically what I said. So now I'm going to use albedo. Often you'll see this as emission, and I'll show you why I don't like emission, and explain that. And albedo again is between 0 and 1, and is a measure of the reflectivity of a planet or a gray body. And basically, this equation is the same one as before with this factor, 1 minus albedo, okay? And so there's your T, then it drops out in the same way, okay? And again, so now what I'm going to tell you is that the entire influence of CO2 is included in this albedo number, okay? So there's no need for forcing, okay? There's no need to discuss that, because let's just talk about albedo, because this paradigm is invalid for us. This doesn't take us anywhere. It doesn't help us more easily understand the world. They might like it because they can do little software programs and they get funding or whatever, but we already have enough stuff. Albedo is where's the rock and roll. The albedo is everything for planet temperature, okay? Now I'm going to talk about this versus emissivity. Now, so there, a lot of people will debate, say, no, you can't use albedo. That we have to use emissivity. Okay, well, okay. So I came across this like yesterday. Hard numbers on the Earth's emissivity are scarce in the climate literature. Okay, well, why is that? This is a critical, number for determining the emissions of the planet. We want to know about what's going on with the planet. We need to know what the emissions are. Well, is this kept ambiguous? What's going on? That's weird. Okay, so I don't like it. And I say, let's forget about emissions. See what happens. Emissions, if somebody wanted to, they could go down a path, an overly detailed path that says, let's calculate the emissions emission constant for the Earth. And they could go and calculate, they'd have to include the emission of a green leaf, the water of a lake, of a house roof, the percentage of urban areas that were highways or roads, blah 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 blah. And each one of these things, well, what about the emissions if it's rough or it's smooth or it's yellow or it's purple? All those things contribute to creating this emissions. And if you were to try to calculate it like that, you're just wasting your time, because in the sun, it would change constantly. So it's a silly idea when we can get the number from albedo from space, and that's what we want to be focusing on. Okay, so technically the emissivity plus the transmittance and reflectance equals 1, but for a planet, the Earth is obviously not transparent. Okay, so we have then we get this equation that we use above. Okay, so now this is important. NASA, when they have a satellite that calculates albedo, they remove the clouds. Okay? The clouds they basically give us the albedo of land when there are no clouds above it, and then they give us this number for albedo of the planet, which has no clouds in it. But that's insane. Okay, so we want to know the general albedo with the clouds, with everything, with CO2 and everything. We can't take out any pieces of the albedo. We have to include a ball. So that's a big mess up. Okay, but we need to correct that, because it can't be doing that. Okay, and so then once we get this albedo number, then we can start to ask ourselves, hey, is the albedo changing? Because if the albedo is changing, then we're going to know a lot already. We're going to know if it's going up, then the Earth is getting cooler. If it's going down, then the Earth is getting warmer. Then we can start to drill down. Then we can start to say, is the albedo changing because it's in this region? Is it changing in Massachusetts but not changing in New Mexico? Are the French, painting everything black, or what's going on? So what's happening? Is there more snow, or are there more clouds? So we can drill down after we see. But if it's not changing, or it's going, we may find that the albedo is rising, in which case it's getting cooler now. But this will tell us, because this will tell us. It includes the CO2, the methane, everything is all in that one number. What we're trying to do here, what the drive is to make a simple, not easy, but a simple model of our climate and our world, so that we can all understand it better and know what is the future. A farmer wants to know, is it going to rain next week? So the people and the governments want to know, is the world warming or cooling, or what's going on? What should we be careful about? How can we think about the future so that we make the right decisions?
So I do have one question here.
Yes, sir, go for it.
So couldn't the global average temperature of the planet change while volcanoes move heat around and the ocean currents change, et cetera? Aren't there all sorts of things going on that could change that surface temperature without any of
Yeah.
this other stuff changing?
Yeah. Okay. So, right. So, one of the aspects of our temperature is I call it the nuclear reactions that are in the core and the mantle. The thorium, for example, has a half-life of practically the age of the universe. So at least half of it. Well, the Earth is 4 billion years, so most of the thorium is still here. So it's down there reacting. There's a huge amount of reactions like this keeping the core warm, and then the Earth is spinning around the core. So there's a huge friction that warms our planet. So some people say, oh, the reason why we're not so cold as Fourier thought is because the greenhouse gas. No. It's because a huge amount of heat is coming from our core. I have talked to people about this, and some of them say, Kevin, are you changing the meaning of albedo? And I say, in one sense, yeah. I want to have a constant number that I can look at to see what's happening. Because if everything is remaining the same, then what am I going to worry about? And you mentioned a volcano. A volcano spews ashes, and those ashes go into the space, and they change the albedo directly, the reflectivity. They might absorb more solar energy. I basically want to know how much solar energy is impinging upon the Earth, and I can do that with satellites. I want to know how much cosmic radiation is coming from supernovas or Milky Way cosmic rays. I want to know that. I want to know the albedo when I look back at the world, and I want to measure all the energy that's leaving. Okay, and so but I've got to have a factor in there that takes all those things and puts them in perspective for me. Then I can start to say, okay, what component of this new albedo number that you're talking about can we digress and then discern some of these other things from? Some, like you said, the volcano is going to say, hey, it could affect. Some, if we all turn on our air conditioners at once, then there's a lot more heat, okay, being generated. Nuclear power. Well, everybody says, oh, nuclear power is clean, renewable energy. Hey, it takes some rocks and turns them into huge amounts of heat. Okay, so if we pretend that heat isn't warming the Earth, we're fools. Wind or solar panels, for example. Solar panels take photons and turn them into electricity. And photons that might otherwise have reflected from the Earth and gone back to space, now they're absorbed by solar panels and turned into energy that's then turned into electric motors whirling around or Tesla automobiles and is warming the Earth. Okay, friction or heat or whatever. So we can say very little about all these different technologies and how they impact the Earth if we don't make a simplified model of what the Earth is. So that's why I use the albedo number. Does that answer your question pretty well?
It does. Thank you. Yeah.
It's not perfect, but what we're trying to do, again, we're not trying to make everything simple. We're trying to simplify the model so we can get out the fundamentals. And it's a methodology of thinking that we have to use sometime to improve our understanding of the world. So back to this historian. So here I show on this Lambert, he came up with this idea in 1760. Well, that's a long time ago, okay? So, but Fourier, in 1824, a brilliant mathematician, suggests the Earth is warmer than it should be. And he said maybe the atmosphere's gases are doing some insulation in it or something. Well, that was in 1824. Stefan and Boltzmann independently basically arrived at the law for gray bodies. Okay, so now we had black bodies, and Planck is in the middle here. We had black bodies, now we have gray bodies. But this is all well after Fourier's work and his suggestion there. And then we start to integrate this albedo concept into this Stefan Boltzmann law. All right, then we have Arrhenius comes along and refers back to Fourier, okay? And he's not really reflecting on this latest stuff here when he starts talking about CO2 and it might absorb heat. He really wants to get to albedo, because if the atmosphere is absorbing, as part of the Earth is absorbing more energy, then it is definitely it definitely is to be subsumed in albedo. You understand? Because albedo is the reflection of the emissivity. So that number then will be a reflection of the CO2, the influence and everything on the planet. Okay, and then Angstrom disagreed with albedo with Arrhenius in 1901. Okay, so Fourier could not have understood that the gas absorptivity should have been included, and the way it was included with the 50 years later in the Stefan-Boltzmann law. All right, now this is kind of important. So now we're starting to ask. Now we're moving into the time issue that I brought up before. So we've looked at the albedo. Now we're going to the next section, the numbers, the second issue. Importantly, photons travel at the speed of light. So anytime we talk about radiation, we're talking about speed of light, okay? This is not like a Sunday afternoon drive, okay? These things are screaming, okay? And I say that a photon can go from the surface to 1/2 the altitude of the troposphere, where 80% of the atmosphere is, about 250 times in 1 second. Okay, so if you tell me that, hey, the CO2 molecule right there, it absorbed some CO2. I mean, it absorbed a photon and re-emitted it. And it's, it did that a long time ago when I started the sentence already. So it's already finished, done, gone. Okay, what's next? All right, so we gotta look at the time when they say, oh, look at the graph. It's shielding, it's stopping, it's already gone again. And importantly, if they talk about CO2 re-emitting photons that return to the surface as radiation, warming the earth. When those photons that are coming back at generally lower wavelengths or lower energy than when they arrive, when they come back, they are absorbed immediately in nanoseconds by the earth and re-radiated as energy by new photons and all across the spectrum. So that CO2 specific wavelength has no merit anymore in the re-radiated energy. So in this manner, and this can happen 250 times a second, or whatever. I mean, this is an approximate number just based upon the speed of the photon travel in the distance. But basically, and then we have to ask, of course, how long does it take to absorb? But we have all this kind of understanding. And granted, the CO2 molecules they can re-emit photons. They can bump, they have elastic and inelastic collisions. Most of the collisions of CO2 are elastic, which means they do not transmit energy, okay? Some of them are inelastic, which means they do transmit energy. Since there's only 0.04% of the atmosphere is CO2, yes, they likely transmit some of that energy from their absorption to nitrogen and oxygen, rather than bumping into other CO2 molecules. But on the time frames, they very, very well may re-emit it, or they could just bounce around for a little while. And even if they did increase the speed of other molecules, their influence is in proportion to their concentration and nothing else. Okay, so now this is evidence during a solar eclipse. This is evidence that most people can observe during a solar eclipse. Temperatures drop 5 to 25 degrees within 20 to 30 minutes without solar energy. So when the moon is hiding our sun, temperatures are just dropping like a rock. So where's the greenhouse? Okay, we don't have one. It's just when we take away the sun real fast, and we can see how little of a greenhouse there is. Okay, so that's really important.
Is the information on this slide, is this a key difference between your thinking and mainstream greenhouse gas thinking?
It is. Mainstream greenhouse does not really fall. See, this is the way science advances. Mainstream is not talking about what happens to the photon after it returns to the Earth. It just says, came back, we're warmer. Now, I'm going to get into the better data in just a second. So I talk those things about evidence, okay? But that's just, I'm getting you guys warmed up here, okay? I'm just bringing you into the broader evidence and the broader reasoning so that I can then nail down the specifics and the details, okay? With real live, basically real time, in the last few days, evidence from NOAA, the National Oceanic and Atmospheric Administration, okay?
Okay, so the re-emission across the whole spectrum, that is a key part of your idea though, right?
Yeah, it has to. It can't. A photon from this CO2 molecule bouncing down to a rock does not bounce back at the same radiation. Okay, it can't. First of all, it's going to lose some energy from entropy. It's going to be absorbed as heat, and I'll explain very quickly. It has no choice. The rate of temperature change is dependent upon the temperature difference as the fourth power. Okay, so that's just the way it is. Okay. Okay, so now we're talking about some more rock and roll here. So this is for Nevada on December 1st this year. Okay, and this is the hour of the day, and this blue one is the energy, the infrared energy only. Okay, that's leaving the Earth, infrared. Not talking about the solar radiation spectrum over there on the left of the graphs. We're talking about the stuff in the infrared area. Okay, so this is the rock and roll discussion here about greenhouse gas. Is all infrared here. All right, so the downwelling is here, the red one. Okay, so basically, interestingly, at no time is the Earth warming from IR. Okay, because always the energy going out is greater than the energy coming in from infrared. This red signal is basically the part of the energy emitted from the Earth being captured, so-called, and coming back to the Earth. But it's always less than what goes out, just as the curve that we show, that blue curve, has space underneath it, right? That's where it's going to outer space, all right? So at all times, and I'm going to further explain this, but at all times, we're finding that this green down here, which is the net IR, is always less than 0. Okay, so and then we've got sunrise and sunset, and so you can start to see this, and I'm going to explore it a little bit. But basically, so at no time is the Earth warming from IR. Okay, here's an example. This is noon, and the upwelling, the energy going out to space is more right now, and so is the energy that's coming down from space, right? So so this is at the surface, this is leaving to space, and this is going out, but not all this leaving made it. Okay, some came down that, and that's that. Okay, so that's the stuff that came back, and that's the stuff that left. Now, even though this is more, this is still higher still, but so so that's how you understand this graph. So it's a really important, and anybody can go see that. Here's the site down here that anybody can read.
Okay, and then a follow-up question on that slide. Then
Sure.
Does this differ from mainstream greenhouse theory, that they can't explain this, or can they?
I don't see any. Look, I can't know everything that everybody's working on all the time, but they don't face this. At no time is the Earth warming from IR. Okay, it doesn't, so that sounds like a challenge to the greenhouse gas theory to me. At no time is the Earth warming from reflected IR that's coming back. Never. It's because there's more IR leaving than going. And so then that's the next thing here. Okay, so now I did a little calculation to kind of put it in a little bit more perspective. So this is just before sunrise, one day in Nevada. Okay. And actually the sun rises in Oxford, which is next door to Desert Rock or whatever. Okay, so this is, I just took a 30-minute square, okay, that's area under the curve, okay, and this is the amount that's leaving. So this is the extra infrared that's leaving the atmosphere, and this is the amount that's coming back, okay? And in this particular instance, in this particular place, okay, if we can think of it like, here's the infrared energy that came back. All right, now this is gone. Okay, it's already gone to space. All right, this came back. Well, if I can make this sliver as thin as I want, let's just call it seconds. Okay, so in 4 seconds, all the IR from the prior 1 second is in space. So bam, there's your greenhouse. Okay, you got 4 seconds worth. All right, and it's, so here it comes, there it's gone, and that's how it works, and that's because at no time is there more IR coming in than is going out. All right, so now I want to look. So this is the same data from a different place. This is Goodwin Creek in Mississippi, which is farther south. So we got to look at our data. Okay, so this is a little closer, but it's always less than 0. Look down here, the net. Okay, but here they get a little closer, and this is during the daytime. Okay, so I orange this out. This is daylight hours. What happens? Okay, so there's more going out than there is coming in, but definitely when it starts getting warmer, it does have more coming down, but it's still got more coming out. Okay, and so that's basically your realities here. Like I said, any IR leaving the planet is only partially trapped by greenhouse gases. This downwelling cannot exceed upwelling. Okay, so this is always lower because it's not sending out all of it. This is across the spectrum, the IR spectrum. Okay, so so there's some qualifications, but it's important. Does that make sense?
It does. And then can you anticipate what arguments people will make against this when they look at this slide?
It's very difficult. I'm introducing this with you now.
Mm-hmm.
Okay. So I can't, I've been making corrections over the week. Okay. So I do the best I can. We are living in a real world and in real time. So I do the very best I can. And that's scientific process. I have to evaluate for the tropics. I want to see that. I really haven't done it. So, but the NOAA doesn't have tropic data. They only have for the United States, which makes sense. Okay, but I would like to see down at the equator, what's the relationship between the upwelling and the downdwelling. Now, I'm going to keep going. Okay, this is an interesting one. Just a nice day in Goodwin Creek, Mississippi. Hey, what's this bump? Well, that's got to be clouds, right? Because this is a nice clear day and they got a little cloud come through. What happens when a cloud hits? Well, upwelling infrared that's getting to space, it's blocked by clouds, can't get as much get out, right? And what happens down here? Well, because there's more blocked to space, there's more coming back from the clouds, you see, because they've been blocking that IR heat. Okay, so that's really clear. This is and it gives you a nice little example of how we can start to understand IR better. Now, I can't say, I know, I mean, just from Professor Lindzen said, he says there's lots of money for, if you want to, I think it was chipmunks or squirrels that he was wanted to, what's the impact on chipmunks, from global warming, you can get funding for that, but can you get funding to evaluate this, because it says that the global warming theory is not valid, that's another issue. So right now, that's, I'm an innovator. I've innovated and I've done it before, and I do the best I can, like I say, but I'm not omniscient. But I can, to the best of my knowledge, they don't get this yet. And so this is a new understanding. This, to me, it's basically clear evidence that there is no warming by returning IR. Okay, so that theory is rubbish. And then that granted, my albedo concept is a little bit novel, and maybe, but if they don't get too upset that the guy comes up with a new idea, I mean, they don't mind buying new software because it's improved. How come they can't buy a new climate science theory, right? Why do they have to hate me? I don't need that. Okay.
So I do have one more question. I don't know if this is the right time to ask it, but I have a quote from NASA here. It says, without carbon dioxide, Earth's surface would be some 33 degrees centigrade or 59 Fahrenheit cooler. Do you want to address that at all?
I say that's absolute rubbish. They're pulling off a Fourier there, and they're going along an assumption. I say that 59 degrees or whatever they said there, I say that all came from our core, and that is big old nuclear reactions and with a half-life of 14 billion freaking years. Okay, because there's that's what's going on, and we are lucky we got that core spinning down there, because those cores spin around, and that creates the magnetic field that protects us against solar winds and radiation and cosmic radiation. So we are a fortunate group of people, world, that we are protected by a spinning core. Mars doesn't have it. Mars is screwed for life, unless you want to, live under a piece of aluminum, whatever it takes to shield yourself. Right? You got to live under the ground. We can live under the ground here. We got plenty of subsurface places to live on Earth. Right? We don't have to go to Mars to live under the ground.
So you're saying there's an enormous amount of heat being generated all the time in the core of the Earth, right?
Yes, sir. Yeah. Yes, sir. They can't quantify. They can't know how much thorium is in the core. How do you know? We're going to drill a hole? Okay. To the core? I mean, granted, I'm not going to say they can't. I mean, I got LIDAR and all these things, so you can't. I'm not omniscient, but from what I've been seeing, they take samples. They look at volcanic rocks. Fine, that's from the crust mantle. But what about the core? How much radiation? What is the percentage of radiation in the subsurface? Or radioactive material? And how much? And so the heavier stuff sinks. So uranium's pretty heavy, so it's down there is what I figure, right? And that's, it's not, the core is of the Earth is as hot as the surface of the sun. I mean, that's rock and roll. Maybe it's not doing fusion, but it's doing some funky business down there, and it's generating heat. Okay, and so that's what I would say. That's the missing thing that they pointed at green gas. I said the greenhouse is rubbish.
One more follow-up question. Do you have a sense as to how warm the Earth's surface would be if there was no sun and no atmosphere at all?
No sun and no atmosphere.
Would that heat from the core come out to the surface then still, or?
Yeah, but it would be gone in short order.
Okay, so let's say atmosphere like we have now, but no sun. Okay. Then what?
No, I say, remember, when you, at the end of the day, you see the sunset, oh, it's beautiful. And then by the morning, it's colder. It's the coldest time of the day in the morning. I say if a black hole, a little tiny black hole just swept through the solar system one day and sucked away the sun, we'd have weeks to live and not more. Because we'd have no more solar energy. Yeah, some of us would burrow under the ground, whatever. We'd have a week or two to do it. And then we would be frozen, and then we'd lose all our plants and everything unless we had some, so hopefully we don't lose our sun.
Okay.
Because
all right.
Our days were numbered, literally.
Okay.
Anyway. This is really important. Heat transfer rates, a rate varies as the difference in the fourth powers of the object and its environment. So the environment is 3 Kelvin. This is just an assumption. It's just for example temperature, okay? And it sort of says though that technically the colder the region, the slower the cooling. So this is a positive 288 Kelvin, which is about 15 degrees. I just use that as an example, about 15 degrees Celsius. Okay, but basically what we're saying then is since the heat transfer rate, this is radiative heat. Now, I'm not talking about conduction or convection. Radiative heat varies as the difference in the fourth powers of the absolute temperatures. The transfer rate, the rate of heat transfer. There's no, the only thing in there is albedo, okay? But the heat transfer rate is just dependent on the temperatures and that albedo number, okay? So we're a gray body because we're not a black body here. Okay, so there you go. So now forcing calculations, and that's everybody's pet thing because that's what they can make a computer and they can charge 500,000, whatever they charge for their software and their grad students to do their forcing calculations and then come up with rubbish models. That's what they do, right? And then they keep lowering and lowering and lowering, as you've shown me. I think you sent me a thing. Anyway, so that's what basically that means, okay? We don't, that paradigm, okay, so is a history of science idea, a paradigm. Basically, the paradigm of forcing is invalid, just as the greenhouse gas theory is invalid. All right, so now this is the third thing I wanted to point out from before. This is important, and this one I haven't seen anywhere in this science. We normally talk about our troposphere as being 12 kilometers thick, but that ain't right. Here's the sun, a long way away. Okay, half the time, well, and at the sunset. It's 385 kilometers through the troposphere. It's sunlight, okay? And overhead at noon, it's 12. So the average of the two gives us our average, even both directions, okay? The average is 198 kilometers, about 200 kilometers. So that's the average distance that a photon is traveling to the Earth from the star. So to explain this number here, it says up here, it says 36.8. This is Raleigh's calculation. I show it more explicitly in one of my papers. But basically, I use a 700 nanometer photon, which is the beginning of the infrared. I use it as the basis of my calculations. And I show through here that 50% of that photon's energy is lost in that travel of 200 kilometers. So what does that mean? It means 50% of the energy is being absorbed by the atmosphere as that photon travels to the Earth through the day. So that's a different figure. So we keep talking about these greenhouse gases doing all this absorbing and bouncing around with the absorbing all this energy because of that little bandwidth. Rubbish. Most of the energy being absorbed from the photons is by Rayleigh scattering. Okay, so now I'm gonna dig a little deeper.
Okay. I'm sorry. Quick question: is water vapor in there anywhere? Or is that addressed separately?
In this thing right here?
Yeah.
No, don't worry about that because that would technically, you could also address whether it hit a steeple on a church or whether it hit a person that was walking down the street. I don't really. This is just what this is pointing out is that let me see what I say here. Some of the thermal energy will be absorbed by clouds. Some of it will be reflected. Okay, So I probably need to think that through. I probably need I probably should multiply it by my, I probably, that's not a bad point. I probably should multiply it by my 1 minus albedo number. Okay, so up to, because some of it's going to be reflected, right? Some of it's going to be absorbed. Some of it's going to be absorbed by this or that. So what's probably is going to be is 70% of that. Okay, because albedo is 30% for the Earth. And that's the old albedo number, not the generalized albedo number for the new climate science. So basically, let's say 35% of all that energy coming from this 700, and 700 nanometers means it's at the low end of the infrared range, which means it has the highest energies. You understand? So that's a high energy one. So the lower ones, so nonetheless, it might be the same. I haven't calculated it, but nonetheless, so let's call it 35% because I should really count. I did this before I did the albedo work. Okay, so I should reflect it in this. Okay, so let me move to the next one. So when I say that the energy that's coming into the Earth and being absorbed by the surface, and then the part that's being absorbed by nitrogen and oxygen, I say it's losing momentum. Okay, these photons. And everybody else, and this is Raymond Pierre Humbert, is a professor of physics at Oxford and lead author in the third assessment report of the IPC. Blah, blah, blah. Okay, he basically says the momentum of atmospheric protons is too small to allow any significant portion of their energy to go directly into translational kinetic energy of the molecules that absorb it. Okay, that's what he said. Okay, well, I don't agree. I did the calculations to show it. Here's Einstein. Einstein says in 1917, in general, one is satisfied with dealing only with the energy exchange without taking into account the momentum exchange. One feels justified because the momentum transfer by is so small that it always drops out. That's what he said. He wasn't doing those calculations. No. But he's right here. Then he says, but for the theoretical consideration, this small effect is on an equal footing with the energy transferred by radiation because energy and momentum are very intimately related to each other. Okay, and that theory may therefore be considered correct only if it can show that this momentum transfer is neglected according to thermodynamics rules. And I show that it's not. That when you travel through 200 kilometers of atmosphere, that number no longer is negligible. Okay, so Einstein here contradicts Pierre Humbert, one of the IPC guys. Okay, the lead author on this third assessment report. I don't know what he does now. I can't keep up with everything. Nonetheless, they dropped it all out, and I say you can't. And that actually makes sense. And it's important to know that both that nitrogen and oxygen are both absorbing energy from the sun, and they're also absorbing energy when it leaves the Earth. And again, this is a 700 nanometer wavelength I did the calculation for. So when it comes and when it leaves, the nitrogen and the oxygen are absorbing, and they are the primary stores of thermal energy in the atmosphere. CO2, its effect is in proportion to its concentration. And this is, just trying to get people back. So this guy is out saying all this stuff and that, and I found other errors with this paper. I can discuss that another time, but I just want to take, for example, this one. But that's a famous paper that I just recently, somebody threw it at me again, and I've already, so I found another problem this week, and it's a good one. And so anyways, but so he's wrong on a number of accounts. They kept telling me, but he is professor of physics at Oxford. He's got a PhD. I don't care. It's what he says is independent of his degrees and his, he could be wrong. And I don't care. I'm not, if I'm going to take this serious, if anybody's going to take this climate science seriously, they have to be willing to disregard everything anyone says if there are ideas that are improvements on our understanding, and we should be willing to adopt new ideas. And that doesn't mean we have to promote ideas that are invalid, but if we assess them within the context of our knowledge and experience, and we don't find them contradictory to reality, it's not about contradictory to other theories. It's about contradictory to reality. Okay, now I'm gonna skip a couple ones real quick, and I want to show you this picture. And it's really not the conclusion. Good, I'm going to make another one.
Actually, could we jump back just to make sure of one thing?
Yeah.
So in the highlighted part in yellow there, is he agreeing
Yep.
with Pierre Humbert there in the yellow part?
Well, that's what everybody thinks, right? He's basically saying,
Yeah.
well, one feels justified in
Okay.
ignoring the momentum. Okay, but then he's got a caveat. This is the last page in this paper, and the caveat says, but for theoretical considerations. But now, so all the and Happer, I had a conversation, an email conversation with Happer, Dr. Happer, and he basically, he says, "Oh, that's not right," and the fact of the matter is, they're making mistakes. And I've found I'm an engineer, and as engineers, we build things that have to work in the world. And if they don't work, and we're using a theory, then there's something wrong with the theory. Okay, that's simple. And so, but in the academic world, in the paper, in order for a theory to work, it has to get accepted by peer review. That's the determinant of a valid theory is if it doesn't contradict anything else in the theoretical world, which has nothing to do with the world. So they're all, and like I said, Dr. Linson confirms this. Okay, so I'm not the only one saying it. So I'm going to go down here. Now, this is not doctor. Now, Dr. Happer told me, ask me if I doctor this. I said, Dr. Happer, you need to get out more. This is a sunrise. I didn't care where it came from. It's just a sunset or sunrise or something. Okay. So, so this is less Rayleigh scattering, and this is more Rayleigh scattering, and this is more still. This is that red shift I was talking about. All right. So this is that 385 kilometers of troposphere. This is about 200 right here kilometers. Okay. And basically, this is red because this white light got shifted, and red is toward the longer wavelength. Understand? Mm-hmm. And this is, you can see, it's going down to the infrared. But basically, because now, if there was a ball of fire there, a ball of sun, and you were looking at it at the end of the or beginning of the day, you can look directly at that sun. But if it's at noon and you try to look directly at the sun, you're crazy. It'll burn your eyes. It'll hurt you. So you don't do that. But at sunrise or sunset, you can look directly at it. That is your evidence that energy is being absorbed. And that is not by CO2. That is by nitrogen and oxygen when their photons absorb the momentum. Now, importantly, Rayleigh or scattering is where a photon goes along and it grazes a molecule. Okay, and in so doing, it transfers momentum and it loses. We know that it loses wavelength and changes color. But we have to acknowledge in conservation of energy that it's losing energy, and it's not going to lose mass because it doesn't have any. It only has momentum, and that's what it loses when it changes from scatter. Okay, so they're false when they all claim that scattering is not absorbing energy. Okay, so I go back to the foundations of the physics and say, what did they say? There's this guy, the newer guy, and this guy, the older guy. This guy agrees with this consorter, but this one said, wait a minute, that's not fully the story here. We got to make sure. Okay, so if you were to say, hey, we got to make sure about nitrogen and oxygen absorbing momentum, well, why? Well, Einstein said so. You might want to, he said we should be very careful before we write off the momentum. Okay. All right. So then I wanted to go here. I don't know if I did the red shift. This maybe I didn't do it already, but this shows that red shift. Okay. Here we got this is your theoretical. This is a common graph. That's why I've used it. So this is your theoretical sun temperature for black body. And there's your actual emission spectrum, and it's shifted to the right. Okay, so what's all happened? This is all the low energy wavelengths. That's a big chunk of energy. Low wavelength is what I meant to say. And it's high frequency, which is the high energy. Okay, so those are high frequencies. That's your ultraviolets and all that. Okay, so that shift is a huge absorption. A lot of people have acknowledged it's Rayleigh scattering, but that's a huge part of the absorption of the atmospheric, of the solar energy. You see how it's shifted right? Consequently, or in addition, the Earth energy, you see again, it's right shifted. Okay, so we can't. So it doesn't just apply to the solar energy, but also to the Earth energy is being right shifted, and just like in the sunset picture. Okay, some of these other things you can look around at these, but I don't want to get too much into all the details. Now I'm going to wrap it up here. Basically, I just made this. All right, this is, if you're going to wipe out the theory, so what is everybody going to think now? So you got to give them something, to occupy their minds with, that they've all been committed to a theory that's no longer valid. Because that's what I'm doing, is assessing the validity explicitly of the greenhouse gas theory. I find it contradicts mainstream physics, and the errors are now clear. Okay, so that's what I'm trying to do here. And if the theory is no good, then you got to throw it away. Now, does it mean that everybody's going to throw it away tomorrow? No, they're going to keep using it. So that, why? Got me. They don't want to change. Who knows? They have a million reasons why they won't change. They're going to think about it. Some of them will, some of them won't. Some of them can handle an innovative new idea. There's fast adopters, and slow adopters, and there's mainstream, so whatever, that's science. Okay. But so this paradigm is this gold temperature line here is taken from the NASA 1999 data, okay, and it's transposed over the solar the sunspot data, okay, which is taken from NOAA, okay. So basically, you have a rising temperature, okay, and then you got a rising sunspot activity, which is solar activity. All right, so here that's kind of an interesting correlation. Now it's not perfect, and again, Zarkova would say, hey, maybe the distance between the Earth and the Sun have an effect on when it went down here a little bit, So it's not a perfect correlation. There are other things involved. So we can't say clearly that it's only the sunspots and strictly correlated with temperature. But it seems to be a lot better pattern match. Now I've cut off the end here because I didn't want to use altered data. I need to get unaltered data. So if I get some unaltered temperature data, then I'm happy to finish off the graph here. But I have a real feeling, based upon buffalo snow idea example, that something's a little screwy, because that ain't global warming. Okay, it's the highest snowfall in their history, I think. And so nonetheless, they say, oh, it's a lake effect. All the snow is lake effect in Buffalo. I went to Ithaca, I went to Carnell in Ithaca, so I know, all the snow is lake effect. But that's why they have big snowfalls, because it's coming over that lake. So why is that any different than 100 years ago when they didn't get as much snow? So something's going on there. So it doesn't look like it's warming. Okay, if it is, ain't warming this year.
Temperatures are graphed there in the gold, showing the 1930s were warmer than 1990s.
Yes, sir. Yes, sir.
Is that U.S. temperatures or global?
Yes. Yeah. Okay.
US.
So I want to clarify that too. Yes, it is U.S. temperatures. Now, it wasn't until the 1950s when the rest of the world really started having enough stations that you could have global data. I don't care what everyone else says. I've looked at it. I really have. In the 1950s, there started to be more and more better temperature records around the world. In this region, there's a little bit in Europe, but the U.S. was the best in this region. They really had the best temperature data, the more exhaustive the state. I mean, there are more stations around, and they were taking this temperature data better. Okay, so I think it's fair to say, look, you cannot say that the Earth is warming and say that no region like the United States reflects the world. So that's contradictory. Either it's sort of the same-ish, or it's not. And if you get the whole United States following a temperature graph, and there was a lot of Tony Heller has again dug up a lot of newspaper articles about really extreme heat events in this 1930s, 1940s region. So it's not as if there isn't historical evidence of global temperatures back when we had no records that are conforming to the U.S. model. So I would challenge the legitimacy of anyone says that this model doesn't apply more generally. Again, with caveats, so it's not perfect, but it's just like we need to be focusing as society. We need to abandon poor theory that's not theoretically well grounded, that contradicts reality. We need to stop accepting invalid data or data that's been tampered in order to conform to theory, and look at the facts. And I know there's going to be a lot of political implications that some people say, oh, screw the greenhouse gas theory. We're just trying to take over the world, or we just want to take all the money and give it to somebody else and take our cut, So I'm sure there are a lot of reasons that people have for doing the wrong thing, but that's not what we want to do. We want to do the right things. We want to keep our science accurate in an accurate conceptual model of the nature of our world and the nature of the universe. So anyway, so that's pretty much my conclusion. And but this is the big evidence that everyone, if they have a clear day, they can go out and look at. They can look right at the sun when it's falling or rising. They can see the colors, and that's not due to just dust. That's due to Rayleigh scattering, the molecules traveling the huge distance, much more than at noon. And that's why the colors of the sky we get is because it's absorbing the photon energy and shifting it red. Does that make sense?
It does, yes. I have 4 follow-up questions, if you have
Super
quick time. First one, you mentioned peer review and indulgences. What does it cost for an ordinary person to try to get something published in a major journal? What's the number?
Again, it's 2,000 or 3,000. What I've seen, maybe more. I kind of focus on the task and not on the peer. I set up the Climate Science Journal in 2017. I'm a grown man. I kind of know the shenanigans. I did grad school at London School of Economics. I know the community. I know how it works. There's a conversation, and I already know how it works. So I didn't submit any of my work to journals. I want to start though, but so I appreciate your opportunity. I'm actually looking right now at getting a PhD in physics. So I'm going to go ahead and take a master's in applied physics, and so I'm working on that. It's not. To be honest, the reason my motive is not to impress anybody with my PhD. It's just to bring my improved scientific method into the formal community. So I don't want to. I don't want to do something that really works and then just leave it outside so that nobody can understand and how to use it, right? So that's sort of my motive there. It's a lot of work and costs a lot of money and time, but that comes with the territory, I guess.
Next one was, I think you're going to get a lot of feedback from this. Are you willing to answer questions to your Twitter handle at all?
Yes,
we
certainly.
Can cut this out. Yeah.
Yes, certainly. In fact, as I said, I'm not omniscient. And as I'm working on this, I assert things and then I come back the next day and I say, is that right? Can I say that? And part of so I have a new theory of induction, which is a basis for a science of innovation. So I apply this theory of induction ruthlessly and rigorously in my innovative tasks. And one of the mental patterns in the behavior of inductive concept formation is to assert the validity of an idea, just so that if you don't assert it, you can't validate it. So I'm happy to receive questions because it will give me an opportunity to improve the validity or prove them as to alter them, or like I said, I'm not omniscient. I do the very best I can, but I have been improving. It really helps to improve, to have conversations with other people, especially the very, very smart people around. I mean, if Dr. Lindzen took a look at this, I sent him something before, he just ignores it. So I'm an Ivy League degree, blah, 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 but, mostly I'm pretty radical. I did this epistemological work in the absence of a theory of knowledge. And that work is really special. And then I validate it in commercial application. That's not the academic way. Dr. Happer was nice enough to respond to me, but he, basically, they don't want to talk to me. They, like you said, and like it's been mentioned, most people, and you've said it, most people do not challenge the consensus. They don't challenge the greenhouse gas theory. And like Lindzen said earlier, where I said in the beginning, they by accepting the theory, they are committing to the narrative. And that's why I said those things in the beginning. So when I challenge the paradigm, this is not light. It's not a light challenge. I'm saying that the professor, the professor at Oxford physics, he's not correct, and that his physics needs some work. Now I'm not saying he's stupid, and I might be a little rough because that's how I am with, I throw the program out. I don't care who wrote it. If it didn't work, throw it out or fix it. So that's the way I'm about theory, and I don't mean anything personally, and I hope these people don't take it personally. And I am a bit rough, like when I say it's the stupidest thing, climate science, for NASA to delete the clouds. Well, it is kind of, but nonetheless, having said that, maybe they didn't think of it, so they're not omniscient either. So I don't want to grate on somebody. On the other hand, if you're not bold with your explanation, then people won't take it seriously. And so again, I don't try and offend anybody, but they think they need to back up and reassess their stance, and then we need to move forward with better science so that we don't make any mistakes that harm people and cost lives, because that's where I see we're going right now.
Okay, so I'll put your Twitter handle for the Climate Science Journal. I'll put it in the show notes so people can get to you. So it's Climate Science Journal is the name, and it's Clim Sci Journal, CLIM Sci Journal, SCI Journal. Okay. Then the next question is there anything that can be done in a lab to verify this stuff? Any lab experiments about the nitrogen and oxygen? Or
yeah, there are.
Okay.
I don't want to necessarily say them all because I know, people will do them, but yeah, there are. I already have some, and but to be honest, I want to better fund. I mean, so if I go down at the bottom here, you go to climate / donate. I haven't, to be honest, I haven't really focused on this or promoted it all. But if people do help me, it will help me because there are experiments that I want to do which help me to substantiate what I've done. You see, I've used a lot of evidence from other people and evidence that nobody recognized before, which, I have to do, but sometimes they can't see the forest for the trees, and so I'm good at seeing the forest sometimes. And but anyway, so yeah, I'd appreciate if people would contribute to my work and help me make sure everything is right and better. So.
I just wanted your comments on this, that there's all these estimates of climate sensitivity that have gone down generally since the year 2000, but none of them are at zero. I just wanted your any comments on that, or you think there will be some coming out?
Well, look, I mean, this guy here
pretty close.
Yeah, and they're getting there, but
yeah.
Look, okay, so let me just restore, excuse me. If CO2 affects the albedo number, right, then it can have an effect, but you don't want to put it in through a forcing equation in a simulation model. And the fact of the matter is, we don't even know what the albedo of the planet is. Nobody does. I mean, you can say, oh, it's 0.29. Really? Nobody really knows that either. Okay, they're kind of like guessing. And to be honest, the best way to determine the temperature of the planet is from the Stefan-Boltzmann law and measuring all the energy that's being emanated. That will tell us the temperature. Because just with the albedo constant which you measure. So anyway, but yeah. So like I say, remember all these people have a vested interest in this paradigm that they're using with this forcing. So this guy, I don't know any of them, but but all of them will say, hey, wait a minute, that can't be right because then my research is threatened. Honest, I mean, it's being frank, And but anyways, it's in time. It's not like this is all going to happen. People are going to start to change and adopt new views and tomorrow. But the sooner people start to use better science, the better off everybody is.
So those studies that show climate sensitivity being almost zero, did they get there in a completely different way than you got there?
I'd have to look at any particular one. In terms of remember what I said, the infrared energy that's leaving is always greater than the amount that's coming. So where's the CO2 doing anything? And see, you could say, but it's leaving slower. And I say, no, the rate of temperature change is dependent upon the difference between the absolute value of the fourth power, right, of the temperature, right? So no, I'm sorry. But then there's a caveat. If CO2 is in the albedo number, then it could affect. But I deleted one little graph of the specific heat of CO2 versus nitrogen and oxygen air. A specific heat capacity of CO2 is lower than nitrogen or oxygen. What does that mean? It means that it takes less energy to raise the temperature. So if you're at a classroom and they shine an infrared light on a container full of CO2, its temperature will rise faster. Not because it's a greenhouse gas, but because it stores less thermal energy, is another way of looking at it, than air in general, or nitrogen or oxygen. It means it has less capacity to melt ice because it has less thermal energy. So the more CO2 in the air, at a given temperature, the less capacity it has to melt ice, for example. So but I didn't want to. I felt I would be talking about too many things. Like I said, it's three things. If I start doing a fourth and a fifth, then everybody goes. So that was the reason I didn't put it in there. But it's important to know that CO2, when you add it to the air is able to store less thermal energy. Not very, very much, because it's a very tiny amount, and the number is not that different, but it is lower. So
I do think that somewhere in one of your things you wrote, you said CO2 could affect the albedo of the planet by changing the growth of plants. Am I right there?
Oh,
But we don't want to get far into that.
yeah,
But
no. These discussions are okay. I would say that right. So green is a real neutral color. So and a desert is more reflecting of energy. So green would absorb more energy, and it does but green absorption of thermal energy does not make the world hotter, or photosynthetic absorption. It actually takes some of it might have bounced back to space, but some of it could have just heated the ground. In which case now it's been turned into carbon life, and which is an absorption. Photosynthesis is kind of cool. It absorbs both photons and it absorbs thermal energy. So it takes heat out of there. That's why the deserts are hotter than the forests at the same latitude, because some of it needs water. You can't grow plants without water too. But the CO2 and water work together to lower the temperature of those regions that are otherwise be really hot. So I say, I've said elsewhere, I think CO2 has a net cooling effect on the planet, both because of the specific heat capacity as well as its role in photosynthesis. And it's not just the plants; it's the oceans full of phytoplankton. So CO2 is the basis of all life on Earth, and so this is like if somebody stood up and a whole group of people said, yes, we can use the tooth of a boar and the eye of a newt, and we can turn iron ore into gold. And they all started saying, yeah, we can do it. Oh, I need an angel's breath, all this kind of, rubbish is what it is. And it's the same scientific community today. It happened, and again, I studied the history of science. So, it's the same thing that's happening today. There's a bunch of people just saying all kind of things, and they're scratching each other's backs, and they're endorsing each other's books and endorsing other funding proposals. And, it's just all rubbish. It's an invalid paradigm is what it's called.
So, yeah, I think we're at a good wrap-up point. Unless you have any other major points to make, anything else to say? Otherwise, we'll go ahead and wrap up.
No, I would just tell people to let the evidence rule, because that's peers asking someone else. And I'll say this because this is a good wrap-up. We are at an incredible point in human existence where we have literally all the knowledge that is available to the planet. A lot of rubbish too. But all the knowledge is available to everyone pretty much as a cell phone, and within seconds or minutes. So the last thing we want to do is depend solely on other people to think for us. The best thing we can do is start to think better for ourselves, because we got all the knowledge there. We're going to ask questions, and we shouldn't be accepting anything just because someone else endorses it. And this challenge you'll find the humanities is now going to be exposed to challenging basic issues in the humanities. And I'll say this is the last statement I'll make. Epistemology is to the humanities what physics is to the physical sciences. It's the conceptual model, the human conceptual nature, and our ability to reason and think and create ideas. So what humans are changes when we understand better what they are. And it has implications for all the humanities: economics, politics, aesthetics, ethics, psychology. All those things have their implications. So the new frontier will be in the humanities, or one of the new frontiers. So anyway, that'll wrap it up. So.
All right. On that note, we'll wrap up. But thank you very much. This is very interesting, and I'm sure you're going to get a lot of feedback. So thank you. All right.
Fantastic. Thank you for having me.
All right. Goodbye.